All right, I guess pretty much everybody's here. Let's get started. I guess I should preface this by saying that this lecture and the next lecture are probably the most sophisticated math you're going to see in this course. It's probably the most confusing, even if it's not the most sophisticated math. So I'm going to try and go very slowly and carefully, and you probably should go over the material a couple of times just to make sure you get it, because it is complicated. Okay, and as I said, it was this one, and then the next time when you talk about the Z transform and the relationship between Laplace and Z, these two parts are probably the most complicated parts. Okay, so what I'm going to do is to go back and review the discrete time Fourier transform and exactly what it is, and we kind of covered that in a bit of a rush, and so I'll go through that carefully. And then I'll cover aliasing, and if you understand aliasing, you understand very deeply what's going on in the frequency and time domains. So understanding aliasing, it may sound a bit exotic, but actually it's very, very important. So we'll go with that. And then I'll talk about what's called the discrete Fourier transform. And I put discrete in quotes because this is discrete as well, but this is discrete in time, and this is discrete both in time and in frequency. So when people say DFT, or if you study any kind of image compression, you heard of DCT, discrete cosine transform. These are discrete time and discrete frequency transforms. And they'll get started with the fast Fourier transform, but we won't go through that. We'll continue with that probably next time. I won't have too much time. Something important going on over there?
I actually calculated questions throughout instead of letting it out to figure out it's the same.
Okay. Don't get distracted. This is difficult stuff. Mohammed Demme. There's no seat. There's one in the back over there. Actually, there are two seats over there. Okay. So first of all, recall that x t written like this is a continuous function of time. And we can imagine it as being some value like this, some continuous function of time. And we don't want to study x of t, but we want to study x of nt, and which is a discrete function of time, like so. And intuitively, you can think of this as being a sample taken every time period, capital T, of some continuous function x of t. And what we do is that we say that x of nt is equivalent to the product of x of t with what we call the Dirac-Coombe, or the impulse train, st of t. In other words, we are going to essentially represent this as these impulses like so. And one can argue that these two are not the same, because x of nt is defined only at these time instants t, 2t, 3t, etc. Whereas this function is a continuous function of time. That's a continuous function of time. So even though they're basically zero in between these time instants, so mathematically these are not the same. All right, mathematically speaking, they're not the same. But as engineers, we'll say, well, we just ignore it for now, and let's just work with this. And this is what we're going to do. We're going to take x of nt and write it as xt, st, t, and it looks reasonable because this is an impulse train, so it's a sampling, and this is what we kind of went through last time. And if you just to remind you, st of t is just the sum of all these impulses. Delta t minus n t. So that's the set of impulses that we have over here, and so we're saying xt is this. So now what we're going to do is we're going to use this, I would say, approximate equality in order to compute the Fourier transform of x nt, the discrete function, using this one. And the reason we can do that is because this is continuous. And so we can, we can define the Fourier transform for that, and that's continuous. And so, we can say, all right, we're going to do the Fourier transform of this over here. Now, the way we're going to do it is we could do it in this way. We could say I have the product of two functions x and y, or x1 and x2, and the product of these two functions is going to be the convolution of their respective Fourier transforms, right? Because product goes to Fourier, sorry, convolution, just like convolution goes to product. So I could do that in about 15 minutes. I will do that, but for now I'm going to do this sort of a quick and a dirty way. And the quick and dirty way is to say that this, given that st is this, we can rewrite xt as equal to sigma n equals minus infinity to infinity x. Okay, let me just do it like this: xt delta t minus nt. Okay, and what we're saying over here is that I have this impulse train, and the value at any value of n is just going to be sampling the x continuous function x at that nt at instant. Basically, I'm going to pick out the value that I have, and if I put it all together, I'll get back this function xt again. Okay, I'm actually right, and maybe I should say xnt. Sorry, I made a mistake here. So xnt. So I'll get the discrete function xnt by doing that, by taking the continuous function and just essentially substituting what st is over here. Okay, that's just substitution. And then I'm going to do the trick, which is where I said the equivalence comes in. I'm going to say this is equal to n equals minus infinity to infinity x of nt delta t minus nt. And the reason is because I'm saying over here that the value taken by xt at the time nt is going to be xnt by definition, right? Because xnt is this one over here is basically going to be whatever. So this is xt, and we're only looking at these points in time, and this matches exactly what these samples are over here. So whatever value xt took, xnt is going to take the same value. So I can't. It doesn't really make any difference when I'm substituting from here to here. And then the next step is to say, well, if you look at this carefully and you look at each individual term, let's say you look at the fifth term. This is going to be x of 5t delta t minus 5t. Okay, look at this term on the left. This term is independent of small t. We have a delta function t minus 5t, and we have some value delta or x of 5t, which is some constant value independent of t. So if I take the Fourier transform of this particular product, this is a constant factor, and that's just your delta. And so this becomes nothing more than x of 5t, and the Fourier transform of this would be e to the minus j omega n t, because we know that delta t, or maybe I should be more precise, delta t minus t naught, the Fourier transform is going to be e to the minus j omega t naught, or the simplest case, delta t goes to 1. So the Fourier transform of the delta is 1, and the Fourier transform of a time shifted delta is e to the minus j omega t naught, where the shifting is by t naught. And in this case, I'm shifting by 5t. So the Fourier transform of that is j omega, in this case 5t. Okay? And we have constant pre-multiplier x of 5t. So the Fourier transform of the fifth term is going to be x5t e to the j omega 5t. And this is true for all values, 5, 6, minus 5, minus million, whatever. And so the Fourier transform of this is going to be sigma n equals minus infinity to infinity x nt, which is a constant multiplier, e to the minus j omega n t. And in fact, since x and t can be represented like this, the Fourier transform of x and t is going to be this over here, which is we define as the discrete time Fourier transform. So let me just go over the steps one more time just to make sure. We start with the continuous function xt, and we say, okay, we don't have a continuous function anymore. We actually have sample function x nt where the sampling values are t. So we have sample values of t, 2t, 3t, etc. And x of t is kind of a virtual thing. We don't really have it, right? We only have this. This is what we actually have. This is what's given to us. And we kind of make up this function xt, okay, as a helper function really, and say that this can be viewed as if it's a product of this continuous function xt and this impulse train st. And then given this, given that st is this value over here, st is delta t minus nt, xnt is xt times this, so this is just going to be xnt is xt times delta t minus nt, and just substituting for xt over here, right? So everybody with me so far? So yeah, this is okay. Now that we have this, I want to compute the Fourier transform of this bit over here. And this bit over here, I just look at one term, let's say the fifth term over here, and I say that the fifth term over here is x5t, some constant, multiplied by the delta t minus 5t, and recalling that delta t minus t naught goes to e minus j omega t naught. This one is going to e to j omega 5t, and so this sum becomes this sum in the transform domain, which is x nt e to the minus j omega nt. And so I just wrote that over here. So obviously this is this, and this transforms to that. So this is the discrete Fourier transform. So each step is hopefully straightforward, but at the end we get something we didn't know what it was, right? Because if I showed you this and said what's a Fourier transform, it's not a continuous function. What do I do? Well, I have showed you how to do it. You have this sort of virtual function, and then you can do this. Okay. Okay. So any questions about this so far? And I have to tell you that the only way you're going to get it is to read it a few times. Like I read this material perhaps 20 times before I got it, okay, sufficiently to be able to write it. And then honestly speaking, before I started teaching this, I had forgotten it because it's subtle. I had to go back and read it like 5 more times, and only then I can explain it to you like this. But it takes time. You have to internalize it, and it's not that easy. Okay, so we call this x tilde j omega, just a new notation. X tilde means that x of j omega is a Fourier transform, and x tilde j omega is, in this case, the discrete time Fourier transform, because your discrete time over here. Now the frequencies, of course, could be anything. We're not saying what the frequencies are. Okay, in other words, we're not telling you what these values are going to be in the frequencies. It could be anything for now, but we're just saying it's discrete time. Okay. And any questions for that? So let's do a simple example and then the homework problem. So a simple example is to compute the discrete time Fourier transform of a to the n u n t 0 less than a less than 1. So we just plug it into here. So this is going to be sigma n equals minus infinity to infinity, a to the n u n t e to the minus j omega n t. And now we just notice that this can be rewritten as, okay, we take unt makes us n equals 0 to infinity, and this is a e to the minus j omega t to the n, right? Just rewriting it. And now this looks like sigma r to the n, okay? And if r is less than 1, we know that this is equal to 1 over 1 minus r. This is just basic sequences. Hopefully you studied this in high school or something like that, okay? So r is less than 1. And, you know, and in fact, what you did not study in high school is r belongs to complex numbers. Then all we need to do is we need that mod r is less than 1. In other words, the magnitude of r should be less than 1. Okay, so, and the same thing holds for complex numbers as well. In this case, it is a complex number. Okay, e to the j obviously is a complex number because it has the j in it. And so this is going to be equal to 1 over 1 minus a e to the minus j omega t. Again, under the conditions that 0 is less than a less than 1. And if otherwise, we're going to have it's not going to converge. It won't be a convergence. So we won't get that summation. So in order for this magnitude to be less than 1, it turns out this is the condition that you need to have. It's a pretty straightforward condition. And the condition is, the intuitive way of seeing it is that e to the minus j omega t is a phasor, okay, of magnitude 1 by definition. And so we have multiplying by some constant less than 1. So the product is going to have a magnitude less than 1. And so we're fine. Okay. Now for the homework, what I said was, and I made a mistake there. I said the function x of nt equals e to the minus what did I say over here? Alpha nt, and I should have added u nt. And the reason why unt is important, of course, is that, or assumed, I guess, is because it's a causal signal. We're studying practical systems, right? We're not studying mathematical objects, studying practical systems. It's a causal signal. So whenever you're given a real system, unt is kind of given. You just have to assume it. But in any case, I did clarify that. And so we plug it in over here. So the Fourier transform x of x j omega tilde of this is going to be sigma n equals minus infinity to infinity. And we have e to the minus alpha nt, e to the minus j omega nt. And this is, of course, using the same idea, n equals minus infinity to infinity. E to the minus j omega, plus alpha t to the n. Now, you have to make sure that j omega plus alpha is going to be magnitude less than 1. And that will be true when alpha is going to be less than 1. So if alpha is less than 1, sorry. I think I guess, you said mod alpha less than 1, alpha less than 1. Anyway, I think 0 less than alpha less than 1 is, trying to remember whether I said mod. Beg your pardon? Alpha the greater than, but yeah, I think, alpha greater than 0, right, because we have the same condition that we want to modulate the phasor down, Okay, alpha greater than 0 is the value, and then we get 1 over 1 minus e to the minus j omega plus alpha t, and that's what you need. And that's for alpha greater than 0. Sure. Yeah. Okay. And hopefully this is what you guys say. I hope you're interchanging your answers before grading them. It would be not a nice thing to grade yourself. Okay. All right. Okay. So at least these two guys are interchanging. They have something going on. Okay. Any questions about this so far? Yeah. Say that again. Delta. I'm just giving you a sort of a. That's R. Yeah, I'm saying magnitude of R is less than 1. Sorry, I'm writing R in 2 different ways. There. Okay. It's a bad habit of mine. I write R and S's in 2 different ways, and sometimes E's as well. So just ask me if you have questions. Okay, so let me now write down the inverse discrete time Fourier transform. And we're not going to really study inverse transform much, but just for completeness, the inverse transform is given by, and just write this down, x n t equals, and that's the inverse. We have x n t, 1 over omega s, integral 0 to omega s, x tilde j omega, that's a transform value, e to the j omega n t d omega. So the form is basically, and then omega s is given by 2 pi by t, 2 pi by t, the sampling period t. So omega s is the sampling frequency, and it's obviously related to the sampling period t as 2 pi over t. And the form is basically, we are going to just go in the range 0 to omega s, and then we have the d omega, and then we multiply by e to the j omega nt, which is very similar to the Fourier transform, where for the inverse transform we multiply by, we do 1 over 2 pi, integral 0 to, well, there the integral range is different, but we're doing x j omega e to the j omega t d omega, right? So it's very similar, except that we have slight changes here and there, and that's, but okay, so it's not super important what it looks like exactly, but that's what it is. Okay, yeah.
So the Fourier transform of a discrete function is a continuous function.
The Fourier transform of a discrete function it's a continuous function. It's a continuous function of time. Yeah. It's a continuous function of frequency. I'm sorry. So even though it's discrete in time, yeah.
The n on the left-hand side
Yeah.
and the summation variable n aren't really the same thing, are they? And put a different way.
Yes, you're right. Yes.
And put a different way, what is the relationship between n capital T and lowercase t?
I'm actually going to put you out of your misery by doing this. This is a common failing amongst people.
Okay, I do like that more. Wow.
Thank you. Yeah, this is still accurate. On this side, the nt is a formal parameter. It's just trying to tell you, by the way, it's a discrete function of time which takes values every t period t. Mm-hmm. And on this thing, it's saying I'm doing a summation. Mm-hmm. And it's a common failing that I don't like in text, and unfortunately, I'm making the same mistake here of reusing variables, as if they're expensive, but they're not. And this is actually exactly right.
Right.
K is probably a better way of putting it.
And lowercase t.
Over here?
Yes.
This one?
Yes.
This is this one x of t is this virtual function xt.
Right, but what is t?
What is t? T is time. T is so we have a discrete function of time, n times the period t. Let's say 1 second, so every second, first second, second second, third second, etc. And we imagine that there is this continuous function of time somewhere out there, which is this t over here, which is the continuous function of time. And so that's over here. And what we're saying is that I can write the x and t as this continuous function multiplied by the impulse train. So I can think of this as what's called a modulated impulse train. I have an impulse train which is all even, and then I'm going to make it go up and down in proportion to x and t, like so. And this is still going to be a continuous function of time. And it's equivalent to, that's why I put this over here, equivalent to the thing over here. This is actually a continuous function. This is discrete. That's why it's equivalent and not equal to. This is discrete, and this one is continuous. Right? And we can't say discrete is equal to continuous. That's why I'm waving my hands here, and I said so. I'm waving my hands here, right? And the equivalence is that at every moment in time that we do care about, they are equal. And which is why in this summation it's valid to replace xt by x and t. And then this allows us to then do the Fourier transform and get basically something that looks like x and t. Because if I had xt over here, what is xt? I don't know what xt is. I mean, that's just a virtual thing. I brought it in and took it out again. Okay, that make sense?
Got it.
Okay, yeah.
After you transform it, the ends are the same on the right side, right?
Yeah. I could call this k over here if you want. And that would be fine too. But then, this is, you can think, as I said, this is just the formal variable. And we got into the same trouble when we did Fourier and Laplace transform. The j omega, it's the same exact thing. We have this formal variable. In this case, we don't have to worry about dj omega, so we don't have to differential. Here, it's just a sum, so it's much less problematic. Yes?
Regarding the last example,
Yeah.
and the homework example,
Yeah.
is it possible to treat the different phasors with different frequencies as numbers? Because when we're using the...
Different phases with different frequencies as numbers. They are numbers.
But there are different frequencies. Can we use something?
Yeah, sure. But you can they cos something and sine something, etc. So yeah, they'll be they're complex numbers and complex functions of time. The complex function, the real parts add up, and the complex parts will add up separately. So when we do the discrete Fourier transform, I'll talk about that in a bit more detail. So, yeah. Okay. Any other questions? Okay, so now I'm going to switch to yellow because I'm going to do the same discrete time Fourier transform, but do it a different way. Okay, and the way I'm going to do it is I'm going to tell you first what I'm going to do, and then I'll do it, and then you'll see what's going on. And as I said, it's high tech, so I have this yellow chalk. Just to show you that it's the same thing, but it's done a different way. So what is a different way? Remember, I showed that this x and t can be, I said it's equivalent to the product of two functions, both are continuous, xt and st. Now, we know, or we should know, that if x1t, x2t are two continuous functions of time, their Fourier transform is going to be 1 over 2 pi x1 of j omega x2, convolved with x2 of j omega. Okay, that's the product convolution equivalence, and I showed that in Laplace. I showed you the product goes to convolution, convolution goes to product, and the same thing is true for Fourier. It's in the text, so I didn't cover it in class, so I'm just kind of telling you this fact, and again, this can be proved from first principles. Okay, so we have this, and so we say, hey, wait a minute, I have a product of two functions over here. Why don't I figure out why don't I use the convolution over there? Okay, so what I'm going to do is to write this. So I want to take the Fourier transform of this product. So I'm going to write over here x of nt, okay, because that's what I want. And over here, I'm going to write this as the convolution of these two things. So it's 1 over 2 pi. And I'm going to have basically the transform of, convolution of the transform of these two things. And I'm just going to leave it parenthesis over here because I need to do some preliminary work before I can show you what that is. Okay, so that's the big picture. I want to basically compute the, I'm going to write it like this. I'm going to essentially compute the transform in this fashion. Okay, now to get there, what I'm going to do is one more trick. And what that trick is to rewrite st in a way that's nicer. Okay, because then the convolution will become easier. Okay, how do we rewrite st in a way that's nicer? Is that we're going to go and re-examine the nature of st. So let me do that over here. So this is st. So basically a bunch of deltas that are spaced in time, and the spacing is capital T because it's a sampling function, right? And that's the Dirac-Coombe, right? Nothing new here. Okay. Now what I'm going to do is I'm going to compute the Fourier transform of the sampling function, the pulse train, or the impulse train, by first doing its Fourier series and then doing the Fourier transform. So I'm going to do two steps. In step one, I'm going to write it as a Fourier series, and then step two, I'm going to do the Fourier transform. Okay, and it'll turn out that there's a good reason for doing it in these two steps. Okay, so how do we write it as a Fourier series? The reason we can write it as a Fourier series is because it's a periodic function of time. Right? It's a period. It has a time period t. I showed you this. So everything is spaced t up like so, and so because it's a periodic function of time, by definition, and it's absolutely integrable and all that, because the integral is 1, it's less than infinity. So I can certainly write the Fourier series like this. I'll say st of t equals sigma k equals minus infinity to infinity ck e to the j omega st, okay, where omega s is where to write that down, the sampling frequencies. Maybe I'll just write this down somewhere on top so we remember what it is. Omega s equals 2 pi by t, and this is straight out of the definition of a Fourier series. If you remember, we had used the term omega naught. We said k omega naught, where omega naught is 2 pi by t naught, and t naught was going to be the time period, right? So t naught is the time period. Here we're using t, capital T. So omega s is 2 pi by t. So this is just the definition of the Fourier series, and all I'm doing is saying it's periodic, it's absolutely integrable, there are not an infinite number of discontinuities, etc. in a finite period, so the Dirichlet conditions are satisfied. Fourier transform exists, in this case it's periodic, it's Fourier series also exists, and this is a Fourier series. All I need to do is to tell you what Ck is. What's the kth constant over here? If I tell you what Ck is, then I've got this Fourier series. So what's the Ck? That is given by 1 over t integral minus t over 2 to t over 2, and I can choose any time period t, so I'm going to choose this time period t, which is minus t by 2 to t by 2, okay, and that's a perfectly reasonable thing to do. St e to the minus j k omega s dt, and this is from the definition of what Ck is. We say that Ck is, the definition is going to be 1 over time period, the integral over this range, x of t times even e to the j k omega s dt. This is the definition of how we get the Fourier transform, a Fourier series coefficient, and this one, I'm going to unfortunately have to go into this space here, is given by just by expanding what St is, or St of t to be precise, is equal to 1 over t integral minus t over 2 to t over 2 delta t minus and t e to the minus j k omega s t dt. Should that be a nt or a, oh, I changed, oh, sorry, I forgot the, okay, I really need more space here. Okay, let me just write this down carefully. It's equal to 1 over t. I have to substitute st properly. Minus t over 2 to t over 2. Sigma n equals minus infinity to infinity. Delta t minus nt. E to the minus j k, and just write ck equals jk omega s t dt. All I'm doing here, by the way, is substituting for st as sigma n equals minus infinity to infinity delta t minus nt. Why? Because that's the definition of the sample train. Right? We define st equals, this is this one right here. Okay, this is just a definition. I just put it in here. I'm just trying to find out what Ck is, basically. Now, the interesting part is that in this particular range, okay, because the range is minus t over 2 to t over 2, in this range, the only value of delta we care about is that delta equal at 0, okay, because at all the other values, basically, it's not even defined. It's not even in the range. The range of integration is just this range over here. And as you can see in this range, even though infinite train, I only have one value I care about, is the delta at the time of time t equals 0. And so this reduces to just this infinite sum over here. Just this, or the integral just becomes 1 over t integral minus t over 2 to t over 2 delta t e to the minus j k omega s t dt, okay, because that's the only value that I care about in that range. And now the other trick I'm going to use is that this range minus t over 2 is some integral, whatever it is, right? And because delta t over here is 0 valued everywhere else, from minus infinity to infinity, I can just as well expand this to minus infinity to infinity, and still the integral isn't going to change, right? And why is that? Because I want to get the formal definition of delta t times something, right? And then I know what that is. That's the easy thing to do, okay? In a minute you'll see why I'm doing that, but certainly it's true that if I expand this range, it's not going to change the integral, because delta t is only going to be defined for the value 0, everything else doesn't matter. So what I'm really doing is I'm basically getting rid of all the stuff over here for the